Hey, what's up, guys? I hope you guys are doing well and staying safe. So welcome to the very first video of a brand new video series dedicated to reviewing some of the concepts for the higher level IB mathematics curriculum. And just as a side note, my content will be more in line with the AA syllabus rather than the AI one, so yeah. But I will definitely be reviewing concepts from both, so no matter which branch you're studying, I hope that these videos will prove at least somewhat useful. Before I dive in, I just want to first give you guys an idea of what to expect in terms of content. First and foremost, I'll be going over the concepts in math that might be a bit trickier, considering that the exams are happening so soon. So that means that my videos will first be focused on proofs, which is mainly going to be induction, as well as vectors, statistics, and some calculus. So without further ado, I'm going to jump straight into induction. So one thing to note about induction is that it's a proof, right? So induction is a method of proof, and it's only really used when you want to prove something over a finite set of the integers, all right? So most of the time, that just means that you won't be working with fractionals or decimals. So in every induction proof, there are 3 steps that you need to know. The first step in induction is known as the base case, and I'll write it down on the whiteboard. Yeah. So the first step is known as the base case, which just means that we're going to prove the statement, whatever statement we're seeking to prove. And we're going to prove that the statement is true for the value at the lower bound of your domain. Most of the time, this number will be 1. And this is generally super easy to do. You just plug this number into whatever equation you're working with, right? Okay. Just write plug in 1. Cool. So step 2 is called the inductive hypothesis. Now in every proof, the step is actually always identical, and it's basically where we just assume that the statement holds for n is equal to k, or whatever variable is you're working with in your statements. So I'll just say here, inductive hypothesis. Oh. Inductive hypothesis, right? So this is where we're just going to assume. Remember, this is an assumption. We haven't proven anything. Assume that when n is equal to k, our statement is true. And of course, this might not actually be the truth, but we're just making this assumption for now. Cool. Hopefully that makes a little bit of sense. If not, I'm going to go through an actual example, so where we actually use these steps in action. So step 3 is called the inductive step. And this is generally the most difficult of the 3 steps. So in step 2, that we assume that when n is equal to k, a random value of k, the statement we want to prove is true. And in this step, what we're going to do is we're going to prove that when n is equal to k plus 1, the statement will also be true. Prove that statement. Sorry about that. It's true. N is equal to k plus 1. And by the way, we're assuming that n is our variable that we're working with in our mathematical statement, but this variable can be whatever you need it to be. So after we finish these steps, we're done. We've proven everything we've needed to prove. But we should first ask ourselves why this works. So how have we just proven our statement to be true over our domain of integers? So by proving steps 2 and steps 3, we're basically saying that If we know that our statement is true for any integer, we also know that it is true for that same integer plus 1. So that's basically all these two steps are saying. All right, in Common English. So in our base case, we've proven that the statement holds for the first integer in our domain. And let's say that integer is 1 because it commonly is. So we've proven our case for when n is equal to 1. All right. And we have a bunch of cases that we need to prove. We have to prove for all n in usually positive integers. Cool. So then by steps 2 and 3, we know that our statement is true for 2 as well. Why? Because remember, we've assumed that when n is equal to k, if n is equal to k, our assumption is true, then we've already proven that when n is equal to k plus 1, our assumption will be true as well. And because 2 is 1 greater than 1, if 1 is true, then by our inductive step, 2 must be true as well. And if 2 is true, we also know that 3 is true by the same reasoning I just used, right? Because 3 is 1 greater than 2, and we've proven that if any integer is 1 more than the last one, and the last one was true, then the next one will be true as well. So n is equal to 3 is true. And we can just keep repeating this argument until we've covered every single case. We've covered an infinite number of cases. It might help to think of it as kind of a domino effect, where we push down the first domino in our base case, and that just ends up pushing down the entire chain of dominoes. So everything else follows. Cool. I'm going to go through a concrete example of what an inductive proof might actually look like. And that might help you guys understand the induction a bit more. All right. Cool. So I'm going to first define a function. I'm going to call it f of n. And I'm just going to say that f of n represents the sum of the first n integers. The sum of the first n positive integers. Sorry, let me clarify. So for example, it would look like 1 plus 2 plus 3 plus 4 plus ... plus n, all the way up to n. So an example is, I don't know, if we substitute n for 3, f of 3 would just be 1 plus 2 plus 3. And I'm going to make a claim. I'm going to claim that f of n is equal to n times n plus 1 over 2. I'm going to say that for whatever n you decide to plug into f of n, this formula will always be true. And to do so, I'm going to use induction. Induction, where our domain of n is all the positive integers. So I'm going to say that for all positive integers n, this holds true. Integers. I'll write a bit in shorthand. Cool. So to do so, remembering back to what I just spoke about induction, there's 3 steps to induction, right? The first step to induction is the base case. And I'm going to just abbreviate, sorry, base case. I'm going to just abbreviate that as BC. And remember what the base case is we're just seeking to prove that the statement is true for the value of n that's the smallest value of n in its domain, right? So in this case, the smallest value of n in all the positive integers is 1, because 1 is the smallest positive integer. So I'm just going to write n is equal to 1, and I'm going to prove that f of 1 is equal to 1 times 1 plus 1 over 2. So what is f of 1? Well, f of 1 just stands for the sum of the first 1 positive integers, right? So that's just going to mean that it's going to be equal to 1, because the sum of the first 1 positive integers is just 1. And what does our formula give us? Well, sorry, our formula is n times n plus 1 over 2. We can substitute each of the n's as 1, and we're just left with 1 times 1 plus 1 over 2 is equal to 2 times 1 over 2, which is equal to 1. And so we see that f of 1 gives us a value of 1, and our formula also gives us a value of 1, which means that for our base case, we can safely say that f of 1 is equal to 1 times 1 plus 1 over 2. Hopefully that wasn't too bad and you guys were all able to follow along. Next, our inductive hypothesis. And every single time we do a inductive hypothesis, we're pretty much going to write the exact same thing. We're just going to say that assume truth when n is equal to k. And that's literally all you have to do for this step. It's super easy. And on the IB exam, if you ever have an induction question, it's just a free mark. And now let's move on to step number 3. Remember what's step number 3? That's our inductive step, right? So I'll just write IS. And that's basically where we say if n is equal to k, gives truth, which basically just essentially means f of k, I'll write brackets around it, is equal to k times k plus 1 over 2. So we're basically saying if this is true, if this statement is true, we're going to prove that n is equal to k plus 1 gives true. So what does that look like? That just looks like we want to prove f of k plus 1 is equal to substitute n as k plus 1. So that's k plus 1 times k plus 1 is just k plus 2 all over 2. Right. So if we know if this gives the truth, then we want to prove that this is true as well. So how do we go about proving this? Well, one key hint is that you always want to incorporate this formula up here, f of k is equal to k times k plus 1 over 2, into proving this formula over here. Now this is really important. All right, so I'm going to go into a new slide and I'm going to prove that this statement is true over here. Okay, so I'm going to rewrite it. One way of writing, okay, let's write out f of k plus 1. So f of k plus 1 is just the sum of the first k plus 1 integers, right? So we're summing 1 plus 2 plus 3 plus ... plus k plus 1. So that's the sum of the first k plus 1 integers. All right, cool. So what we can do is we can say, hey, look at the first k integers. Notice how the sum of the first k integers is simply equal to f of k, right? Because f of k is the sum of the first k integers as well. So we can write f of k plus 1, therefore, as f of k plus k plus 1, because k plus 1's, we missed k plus 1 at the end, right? Well, and from our inductive assumption, what did we assume? We assumed that f of k is equal to k times k plus 1 over 2. So we're going to use this assumption, and we're actually going to plug this value of f of k into our equation here. So plugging this in, we have k times k plus 1 over 2 plus k plus 1. And here, what we can do is we can notice that, hey, there's a k plus 1 on the left term, there's a k plus 1 on the right term. We can factor out the k plus 1. So we get k plus 1. And we have what's left over, k over 2 plus 1. All right. So we did a little factorization. We can write 1 as 2 over 2, and we can simplify the fraction on the right term. And we're just left with k plus 1 times k over 2 plus 2 over 2 is simply k plus 2 over 2, right? And finally, we can bring this divided by 2 term outside. That's supposed to be an arrow. And we're simply left with k plus 1 times k plus 2 over 2. And this is exactly what we're looking for, right? Remember in our last slide, we wanted to prove that f of k plus 1 is equal to k plus 1 times k plus 2 over 2. And we were just able to do this. So then we can say that f of k plus 1 is equal to k plus 1 times k plus 2 over 2, which means that we've successfully proven our inductive step and our induction is complete. So hopefully this video on induction made a little bit of sense. Next video, I will be going over some actual examples from past IB papers.